Okay, so final topic for Unit 8 is buffers. And this brings together everything we've learned about weak acids and weak bases and the way that they interact. So let's jump right in. Maybe. Okay, here we go. All right, so buffers really rely on that common ion effect. And you guys remember when we talked about equilibrium that when we had a common ion, that caused a shift in the equilibrium reaction. So a buffer relies on the fact that the common ion effect can kind of help us in this circumstance to keep the concentration of hydrogen ion and therefore pH very, very stable. So first let's talk about what we have to have in order to have a buffer. So a buffer is a solution, and that solution needs to contain two things. It needs to contain a weak acid and its conjugate base, or it needs to contain a weak base and its conjugate acid. So it's a weak conjugate acid base pair. Both pieces have to be there. Now, usually the conjugate is provided in the form of a salt. So for example, we might have acetic acid, and the conjugate base part would be provided by a sodium acetate salt. So we would have to have both acetic acid and acetate ion. So because buffers have this common ion effect working for them, they are very resistant to pH changes, even when strong acid or base is added. So let's talk about how that works. So if we have a conjugate acid-base pair. In this case, we're talking about hydrofluoric acid and the fluoride ion. So we have an equimolar solution of hydrofluoric acid and sodium fluoride. So if we add a small amount of hydroxide, even a strong base like hydroxide, that hydroxide ion is going to react with the hydrofluoric acid, and it's going to make the fluoride ion and water. Now notice that the hydroxide ion isn't reacting with the hydrogen ion that's in solution. It's reacting with the hydrogen fluoride. And so the pH of the solution doesn't change substantially. Now we could make the argument that it's reacting with the hydrogen ion, but because we're at equilibrium, if it reacts with the hydrogen ion, the hydrofluoric acid is going to dissociate and bring that hydrogen ion concentration back to where it was before. And so when we add that small amount of hydroxide ion, it decreases the amount of hydrofluoric acid present, it increases the amount of fluoride ion present, but it doesn't really change the amount of hydrogen ion present. In a similar fashion, if we added acid, so we add hydrogen ions, the fluoride ion is going to react with the hydrogen ion to form hydrofluoric acid and water. Again, not changing the concentration of the hydroxide ion substantially or the concentration of hydrogen ion substantially. And so because of that common ion effect, whether we add acid or base, the pH of the buffer is not going to change substantially. So it's important to recognize what we have to have in order to have a buffer, and it's important to understand what are the reactions that account for its buffering ability. So let's take a look at a practice question. So we have the acid ionization equilibrium for hydrofluoric acid here, and our student says that if we have a solution that has 10th molar hydrofluoric acid and 10th molar sodium fluoride, it's only going to change slightly if we add a small amount of acid or base. So what are our two equations? Well, they're the two equations we just talked about. They're hydrofluoric acid reacting with hydroxide ion to form water and fluoride ion, and hydronium ion or hydrogen ion reacting with fluoride ion to form hydrofluoric acid and water. And that pair is choice D. So make sure when you're trying to account for how this works that you're talking about the reaction of hydroxide ion with undissociated acid and the reaction of hydrogen ion with the conjugate base. Okay, so I think you guys should be pretty good at identifying what is a buffer. That was one of the things that we emphasized a lot in honors chemistry. But if you have questions about that, I'm happy to answer them. Now let's talk a little bit more about calculations with buffers and understanding the pH of buffers, because this is definitely something we did not talk about in Honors Chem. So we talk about the dissociation of a generic acid. We know that Ka is equal to the hydronium ion concentration times the conjugate base concentration over the weak acid concentration. We also know that we can take that apart and we can get that the hydronium ion concentration, the negative log of that, is pH. And so if we want our pH to change as little as possible, we want the ratio of the conjugate base to the acid to be as close to 1 as possible. And so because we want as much of this and as much conjugate base available to react with acid and as much acid available to react with conjugate base as possible. So we're going to get our maximum buffering when that ratio is close to 1 or when pH equals pKa. And so we can choose a buffer system based on the pH range in which we want it to buffer. And so we're going to choose an acid whose pKa is close to the desired pH. If we look at the human body, we have actually 2 buffer systems in our blood system, and both of those are there to keep our pH of our blood at a particular, very strict range. And so that's why we actually have 2 buffer systems. Okay, so how do we calculate the pH of a buffer? Well, if we have equimolar amounts of a weak acid and a salt of its conjugate base, the pH of the solution equals pKa. This sounds familiar, right? We learned this about the halfway point of the half equivalence point of a titration, and that's because we have equimolar amounts of the weak acid and its conjugate base, which means that our pH is going to equal our pKa. And so that region of a weak acid strong base titration or weak base strong acid titration, we call a buffer zone, because we're at a place where adding that doesn't make significant changes. So if we have equimolar quantities, then the pH of the solution will be equal to the pKa of the weak acid. So for example, if we wanted a buffer with a pH of 9.14, we could mix equimolar amounts of boric acid, whose pKa is 9.14, and sodium dihydrogen borate, which is the salt of its conjugate base. How do we calculate the pH if it's not equimolar? If we don't have equal quantities of the conjugate base and the acid, well, that's where the Henderson-Hasselbalch equation comes in. And we talked about the Henderson-Hasselbalch equation already. Its pH is equal to pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid. So we are going to go through an exercise here. We're asked to find the pH of a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate. So the lactate is the conjugate base of lactic acid. And so we're going to use the Henderson-Hasselbalch equation. And we're going to pause this for just a second. Actually, we'll go here to the board. So we are going to use the Henderson-Hasselbalch equation. So we have pH is equal to pKa plus the log of the base concentration over the acid concentration. And we're given that the concentration of lactic acid is 0.12 molar, and the sodium lactate is 0.10 molar. And we know that the Ka for lactic acid is 1.4 times 10 to the negative 4th. So we're going to have negative log of 1.4 times 10 to the negative 4th plus that. So grab a calculator quickly. So we have the log 0.83 plus so and we have 3.85 and we get that this is equal to 3.77. And so that's how we would find the pH of that buffer. Okay. Let's jump back into our slideshow here. Whoops. Maybe. Try that again. There we go. Okay. This exercise is a little bit easier. We're not going to need a calculator for this one. So we have, again, a lactic acid sodium lactate buffer solution. We're mixing 40 milliliters of half molar acetic acid with 200 milliliters of 1 molar sodium acetate. Oh, that's not acetic acid, sorry. And we're given a pKa. And we're asked to find the pH of the resulting solution. Well, we know we're going to use the Henderson-Hasselbalch equation. This time we're given pKa is 3.08. So we know that it's going to be pKa 3.08 plus the log of the concentration of the base divided by the concentration of the acid. So we need to figure out what those concentrations are. So we would multiply the volume by the molarity and divide by the total volume. So 200 times 1 divided by 240. We have 40 times 0.5 divided by 240. And those two are over each other. We can cancel out the 240. And we're going to be left with base over acid. So we have 200 over 20. So we have, did I do that right? So we have the log of 200 over 20, which is 1. And so pKa of 3.08 plus 1 gives me a pH of 4.08. And yes, this is a multiple choice question. And yes, you can be expected to do that without a calculator. Okay. So last concept then when we talk about buffers is this idea of buffer capacity. And what buffer capacity is the amount of acid or base that can be added to a buffer system without changing the pH by more than 1 unit. So we're talking about kind of a zone where it's keeping the pH relatively constant. The higher the concentrations of the acid and the conjugate base, the higher the buffer capacity is going to be because we have more available to react with whatever's being added. So the higher the concentration is, the higher the capacity is. The other piece of this that we want to think about is the idea that if the ratio of conjugate base to acid or acid to conjugate base is not 1-to-1, the buffer is going to have more capacity in one direction than another. So if you have a higher initial concentration of acid, it's going to have more capacity for base. If you have a higher initial concentration of base, then it's going to have a higher capacity for acid. Also, if it's not 1-to-1, that's going to affect that initial pH of the buffer system. It's not necessarily going to be at pKa, it's going to be at pKa plus the log of the concentration of the base over the concentration of the acid. So let's look at two exercise problems here. So we have the acid ionization of acetic acid, and we have, we want to make a buffer, and we're going to prepare our buffer by combining acetic acid with sodium acetate. But our student mismeasures the volume of the sodium acetate. So they actually use 76 milliliters instead of 75 milliliters. So what do we know? We know that we're going to have more base than we should have had. So that means that the pH of the buffer is going to be just a little tiny bit higher, because we're going to be taking a log of a number that is more than 1 instead of a number that is 1 or less than 1. So our pH of our buffer is going to be slightly higher. And then, so what are we looking at? We should have a pH that's higher, and we also know that it's going to have a slightly higher capacity for acid than for base, because more base was added than acid. And so our answer is D. Okay, this one asks us to consider both, I think. So our student is we're again making a buffer by combining an acid and its conjugate base. We're combining this time hydrofluoric acid and sodium fluoride. So if instead of mixing 250 milliliters each of 10th molar hydrogen fluoride or hydrofluoric acid and potassium fluoride, they mix 250 milliliters each of 0.05 molar hydrofluoric acid and potassium fluoride, what's going to be the result? Well, we're going to have a lower capacity, because we have a smaller number of moles of hydrofluoric acid and of the fluoride ion. And that's going to lower the capacity because there's fewer moles available to react. And so we're going to choose A. Okay, so that's it for buffers. We'll continue this conversation tomorrow. As always, if you have any questions, let me know.